Hello everyone, welcome back to Bikes of CC. So in this lecture, we'll check that if a relationship decomposition is lossless. Now, as we know that usually in database management system, sometimes we decompose a large relation R into several parts. So say we have a relation R and it has been decomposed into n parts, R1, R2 to Rn. Now, ideally, if you join those relations R1 to Rn, you are supposed to get back this original relation R or the parent relation R. If by some means we find that the number of tuples after joining the child relation, that is R1 to Rn, if the number of tuples is greater than the number of tuples in the original relation R, we will consider or we will mark those type of decomposition as additive or lossy kind of decomposition. So here we will learn a technique to find out that if a decomposition is a lossy kind of decomposition or a lossless kind of decomposition. Now if the number of tuples in after joining these relations is equivalent to the number of tuples of the original relation R, that type of decomposition is known as lossless decomposition. So say we have a relation R which is composed of SSN, ename, pnumber, pname, plocation and Rs, and we have the functional dependencies of the original relation R as SSN gives ename, pnumber gives pname and plocation, and SSN and pnumber together gives the Rs. Now we decompose that into this R into three sub-relations R1, R2 and R3, where R1 consists of SSN and ename, R2 consists of pnumber, pname and plocation, and R3 consists of SSN, pnumber and Rs. Now we are to find out that if this kind of decomposition is a lossless or a lossy one. So let's get started. So the first step will be, we'll create a matrix M such that each row represents each decomposed relation and each column will represent each attribute of the parent relation R. So let's do that. So see here, each row is created corresponding to R1, R2 and R3 as per the decomposed relation. And now these attributes or these column names are the attribute names of the original relation R. So we have SSN, ename, pnumber, pname, plocation and Rs. So this pnome corresponds to pnumber and ploc corresponds to plocation. I hope you understand that. It's for the space constraint I have used pno and ploc. Now the next step is, for each row mark the attribute column as A whenever the attribute of parent matches with the row. Now these were taken from the parent relation R. Now R1, the attributes of R1 are SSN and ename. So we mark SSN and ename as A for R1 or row 1. Now each row corresponds to each decomposed relation. Now R2 consists of pnumber, pname and plocation. So now pnumber is marked as A, pname is marked as A and plocation or ploc is marked as A for R2. Now we consider row number 3 or R3. R3 has attributes SSN, pnumber and Rs. So we mark SSN column as A for R3. Then we have pnumber. So this row also will be marked as A. This column will also be marked as A. And then we have Rs. So this column corresponding to Rs for this row is marked as A. Now we move on to the next step. Now consider each FD X gives Y. Where am I? Okay. just a moment here. So each FT, X gives Y of the parent R, and consider those rows with column marked as A for each attribute of X. Now X gives Y is one of the, we have to consider each functional dependency. So let's try to understand up to this. So the first functional dependency, say we consider SSN gives ename. So in this case, your X is the SSN and Y is the ename. So then it says, consider those rows with column marked as A for each attribute of X. Now, X has only one attribute for functional dependency number 1, that is SSN gives ename. So we have to identify those rows whose SSN column is marked as A. Now we have R1 and R3 who have their SSN marked as A. So now we are not considering R2 for now. We will consider only R1 and R3 for this case. Next it says, consider the attributes in Y one by one. Now now this Y contains only one attribute in this functional dependency, that is ename. So we consider this ename now. If any of the columns corresponding to a Y attribute is marked as A for any row, mark the same column of the other row with same X as A. Now we are considering only R1 and R3 in this functional dependency. So we have to see that if this Y attribute, here it is only one attribute ename, if this ename column for R1 and R3, if any of these columns, if any of these rows contains the ename column marked as A. So in this case we have R1 which has the ename column marked as A. Now since this R1 has this ename column marked as A, now we will say that mark the same column of the other row as A. The other row in this case is R3 only. So since this is already marked as A, we will mark this as A2. Alright. So this will now continue. Then we move on to the next functional dependency, that is P number gives P name and P location. Now let's find out the rows which have their P numbers marked as A. So now here R2 and R3 have their P numbers marked as A. So we will now consider R2 and R3. So the first Y attribute in this case is P name. Now let's find which of R2 and R3 have the P name marked as A. So we have R2, this row R2 which has the P name marked as A. Now since this is marked as A, we will mark the P name column of R3 also as A. Now here the thing is, if this was not marked as A, you couldn't have marked this as A. You had to leave it blank. Okay, next we move on. The next Y attribute of this functional dependency, that is P number gives P name and P location, is P location. Now we have to check that which of the rows contain their have their P loc marked as A. So we see that R2 has the column P log marked as A. Therefore, we will mark the column P log of the other row, that is R3, also as A. Now see, this row R3 has all A's in it. Like we don't have any blank in this R3 anymore. Next we move on to the next criteria or next part, which says that if at least one of the rows have all the columns marked as A, that is there are no gaps left, the decomposition is a lossless join decomposition. So now R3 has no gaps. So now you can conclude that this decomposition, that is decomposition of R into R1, R2, R3, is a lossless join decomposition. In a nutshell, what we did is we have created a matrix first. Then we have marked the attributes according to the row, that is the child or the sub relations of the original relation R. Then we mark the attribute according to the relevant FD for matching rows only. So whenever the X attributes matched, we had considered only those sub-relations, and we have marked the attributes accordingly. And if all the columns were marked as A for at least one row, we concluded that this is a lossless decomposition, otherwise it's a lossy decomposition. Now let us move on to another example for the same we will try to find out that if this is a lossy or a lossless decomposition. See, here we have the same relation R with SSN, E name, P number, SSN, E name, P number, P name, P location R's, and we have the functional dependencies, SSN giving E name, P number giving P name and P location, SSN and P number giving R's. And then we have two decomposed relation, R1 which contains E name and P location, and R2 which contains SSN, P number, R's, P name and P location. So first we'll create the matrix. Now for your relation number 1 or the first row, you have the attributes E name and P location. So mark this column E name as A in R1 and also P log or P location as A. Now we move on to this relation R2 or the row R2. So R2 contains SSN, so mark this SSN column as A. P number, mark this as A. Hours, this is also marked as A. P name, mark P name as A and P location as A. Now we have to check the functional dependency part. So the first functional dependency, SSN gives E name. So this is your X and this is your Y. So now we have to find those rows which have this SSN column marked as A. So in this case, we have just R2 marked as A for your SSN column. So R1 doesn't contain this SSN marked as A. So we cannot consider this functional dependency. Next, we move on to the next functional dependency where P number gives P name and P location. So this is your X and this set together is your Y. So let's find out those matching rows which have their P number marked as A. Now in this case, R2 has P number marked as A, but R1 does not have their the P number marked as A. So we cannot consider this functional dependency. Now let's move on to the third functional dependency, which says that SSN and P number together gives R's. So this whole set SSN and P number is your X and hours is your Y. So in this case, we will have to find out those rows which have their SSN and P number, both SSN and P number marked as A. Now R1 has SSN and P number marked as A, but R2 has SSN and P number marked as A, but your R1 has gaps in both the columns. Now R1 also had to have this had to have this SSN and P number marked as A for further consideration, but it does not have that. So we cannot consider this functional dependency also. So now there are gaps in your table. There are no more functional dependencies left and there are gaps in your table. So we can conclude that this is a lossy decomposition or an additive kind of a decomposition. So that was all for today. I tried to simplify the process as far as I could, and if you like my video, please give me a thumbs up and share it with your friends.